Welcome back everybody into this second video on the setting up of a template on a Siemens ET200 PLC for tasks associated with the automation discipline of the World Skills Competition. So in the last video we finished off on the screen here, and the last action I took, I believe, in the last video was to create the tag table for the digital inputs and the digital outputs. So if you didn't see the first video, I recommend that you go on ahead and look at that first before proceeding into this video, because I am going to be building this on a piece by piece basis. So in this second video, I'm going to proceed ahead now, and I'm going to add in our first block. The first block I'm going to add in is going to be called My Data. It's just what I call it. You can call it whatever you like, and this is going to be a global data block. Okay, I'm going to leave the numbering of this block in as automatic. It's going to choose the first number. Obviously, this is my first block that comes in. It's going to default to number 1. That's fine for me. Okay, and here's my data block in here. Now I'm going to populate this with a couple of things first, and from that then I'll explain what we're doing. So the my data block, if you think about it like the filing cabinet for this whole entire PLC program. And this filing cabinet has multiple drawers in it, and in each drawer I store different information of different parts of the PLC. So in my first drawer, my top drawer here, I'm going to store all the data that has to do with management. Now, what kind of data does management have? So within that management drawer, I'm going to have file separators, for instance, and this here is going to be UDT management. So in this filing cabinet, in the top drawer, I have in my first file divider, it's going to store the status, the safe status of my system, what run mode I'm in, what run sequence I'm in, what timers and what counters I'm in. This is where I need to store the data. So the UDT that I created, in which I put in them different data types, needs to read and write. Right, that's what we use them for. And where do I read from and write to? Well, it's this filing cabinet. If the PLC wants to know what's going on in any place in the code that it doesn't have access to within its own function, it just goes to the filing cabinet and looks. So I will have management. I'm going to store the status of all my digital inputs in here as well. DI, UDT DI. Indeed, my digital outputs will also be stored in here. DQ. And all my sequence data will be stored in here. So for instance, if I'm in sequence 1, what step am I in? If I'm in sequence 2, what step am I in? So for this one here, I'm going to go for seq_1. Why don't I use a numerical number 1 as opposed to the letters 1? We'll explain that maybe a little bit more when we get into the management block. But to be honest with you, and straightforward with you just now on it, is that whenever you're coding in SCL, you use copy and paste a lot. And when you paste, obviously you have to delete out certain characters and replace them with new characters for the next task, if you like. In a lot of cases, that's deleting out a 1 and putting in a 2. So for instance, the sequence 1 to the sequence 2, or timer 1 to timer 2. I don't all the time want to delete out sequence 1 stuff and change it to sequence 2 stuff. So if that was a numerical 1, it's very easy to delete that 1 and replace it with a 2, where I don't want that to happen in a lot of cases. Right, yeah, I can add in sequence 2, sequence 3, sequence 4, but before I do that, what I'm going to do is, sorry, yeah, I have to change my UDT here. What I want to do is I want to pre-populate some starting conditions for specifically my timers and my counters within sequence 1. So what I mean in that, for instance, in timer 1, I'm going to leave that blank to be 0 as a start value. However, let me see here. I have a timer 1. I shouldn't have a timer 1 in there twice. Let me just go back up and refix that UDT. PLC data types, sequence. Must have been when I did my first copy and paste. I have a timer 1 and then another timer 1. I should not have that timer 1 in there. I should have timer 1, timer 2, timer 3, step and function, 4, step and function, and so on. Grand. Just make sure the counters didn't do the same. function. Yep. Yeah, it looks better now. Now, after you create a UDT, I should have did this in the first video, but I'll do it just now. If I go into my data here, it's going to come up with a pink field, because once you establish the UDT and you write that into your kind of your PLC's DNA, whenever you change it, what you must do is you must recompile to propagate them changes throughout the whole entire code. So to compile, what I do is I click on to the PLC name and click compile. I will get a couple of warnings down here, hopefully no errors. 3 warnings. These warnings will disappear the next time I compile, but the first time you compile after setting your security the way we set our security, you're going to get these warnings, which are, for instance, that the OPC UA server has been enabled and we do not have, we have unsecured communication allowed, as well as no user authentication required. So that's why them errors come or warnings come up, but you shouldn't have any errors at this stage. If you have an error, it's worth going back and checking it. Well, it's not worth, it's mandatory that you go back and you check it, because you won't be able to download to your PLC with errors. But as I said, the warnings will disappear the next time I go around. However, after do the compile, you see that pink field has now reverted to the default Siemens color. And now I have timers 1 and that separate timer 1 went away. So what I do in all of these here, just for a template, is I pre-enter a value in here. Now historically in World Skills tasks, there has been 1 second dwells. The odd time there'd be 2 second dwells and so on. I tend to write these all in as 2 S's, 2 seconds. All right. So I'll do this again on the next one. So just to make it a wee bit clearer on what I've done. So in timer 1, I've opened up the function, which is the part of the timer that I'm coding in the code. The PT is the preset time, and I'm going to default it to be 2 seconds for timer 1. I'm going to do the same thing with timer 2. So again, W step, I don't change that. The function, the preset time, is given here in this IEC format, which is T hashtag 0 MS. So if you change that 0 to a 2, now you're dealing with 2,000ths of a second or 2 milliseconds. Make sure you take out the M, T hashtag 2S. That's now 2 seconds. Okay. The other thing there that you could do, if you like the M and you want to get 2 seconds, is indeed put in 2,000 milliseconds, which is also 2 seconds. All right. But I'm going to keep this in seconds. You have to keep the T hashtag and the S at the end as well, just by virtue of the fact that that is the IEC formatting for it. All right, so 2 seconds. This is a wee bit of a lengthy process, and I appreciate you sticking with me on this. I will pause the video for the next kind of run of adjustments that I'm going to make after I show you what it is, to save you having to forward past all this. 3 seconds function and Pt2s. Alright, so every timer that I now have in sequence 1 is defaulted with a start value of 2 seconds. I do something similar with the counters, except in the counters here, my check step, my increment step, my reset step, I'm going to leave blank. I'm going to write that in code because they are very specific and they do tend to change an awful lot more than the amount of counts that we need to do. However, in the function, I have count up, count down, and my reset, my outputs, my preset values, my current values, and so on. In this one, the only thing that I look to change is change my preset value. So preset value is how many repeats of that subsequence, that counted sequence, do you want to do. That could be 2, 3, 4, but typically it's 2 or 3 just for time reasons, and obviously it can never be 1 or it's not, there's no need to count. I'll always put this to 2 as well. All right, so that's the preset value, the PV, in the function for each counter. Same in counter 2, into the function, preset value, let's put that to 2. All right, so what I'm going to do is I'm going to pause the video and I will change each one of these here to 2, and then I'll restart. Okay, everybody, back again. I'm just going to make my last change here for preset value to be 2, and that's them all done. That's all 8 counters. Forgive the voice, by the way. I have a slightly dosed, so please bear with me on that one. All right, so there is each one of them now done. Okay, now I can feel free and I can add in further sequences if I want, right? So what I will do is maybe Control C, or let's just add a row underneath that. I'm going to Control C, Control V, call this sequence 2, right? So I was very careful to make sure, paste that again, sequence 3, to make sure that I updated or that I changed the PV value in the in the timer, or the excuse me, the PT value, the preset time value in each timer in sequence 1, and indeed the count values there as well that I wanted in each counter in sequence 1 before I copied and pasted, because when I did that, what it's automatically done now is that in any of these timers, it's carried that value through for sequence 2 and sequence 3. So now all timers in sequence 1, sequence 2 and sequence 3 are preset to 2 seconds, and all counters in sequence 1 through sequence 3 are indeed set with a preset value here of 2. Right, and I'm going to close that off just now. All right, so that's all I'm going to do just now with my data block. Indeed, there is more drawers in that filing cabinet, but at the minute, as I said, this is for automation, is focused on the regional tasks. You can do just about everything in the regional tasks with them. I'll say just about everything. You can do everything in the regional tasks just with what we have in that my data block. Okay, the next thing I'm going to do is bring in our first block here to code. So in this one here, I call this the CP underscore interface. Right, CP. I'm taking inspiration for CP from the Festo CP lab, meaning cyber physical. So in this this function, right, that I'm going to write. It's a function, make sure not function block. It's a function. If I create a function block, it's the same interface, except it creates a separate data block, a separate mini filing cabinet for the data belonging to that function. I don't want that. I want to put everything in my main filing cabinet in the my data. So I'm going to write a function, and I'm just going to point that to the my data block. Indeed, it is SCL, right, which is our structured computer language. And this is what we're going to code in. Now, what is the CP interface? Let me just create that. In the CP interface, what I'm going to do is I'm just going to first drop that down, get some more real estate here in my coding section. I need a function to be able to convert or to be able to transfer coded requirements, which are generally outputs. I'm going to tell the code, right? I'm going to say, if you do this, that, and the other, then I want this output to go high. And the output that I want to go high is the data output. It's the one that's in that UDT DQ. I'm going to set that value to go high. Now, that value going high is just going to be reflected in the my data block, right? So for instance, DQ, I might say here, I want this output here to go high. All right. But so what? It's going to show up there in the DQ as going high, but it won't do anything physically until I get to this block. And I want this block here to monitor the my data block. And I want to say in this block here, right, if an output goes high, I want you to emulate that. I want you to then send the actual wired output high. I want you to turn the pin on, the associated pin that's on that digital output card. I want you to make that true. I want you to put 24 volts there, because if I get 24 volts there, then whatever's wired into that will get a 24 volt feed out and it'll operate. So some sort of a coil, maybe a light, maybe a relay, a motor, whatever it might be. And similarly for the inputs, I'm going to do the same thing. I'm going to ask this block here to monitor the pins on each of my input cards, so that if any of them go true, if I see 24 volts in any of them, I want to tell the data block here there's something coming in on that input. So I'm going to write the associated cyber or data input value to be high or low or true or false, depending on what the outside world is doing. All right. Now, how do we do that? So first thing I'm going to do is I'm going to copy each one of these. Right. So I'm going to select IP0 to IP15, just like that, and hit Control C. Right. I'm going to come back on into my CP interface, go into my input up here, and hit Control V. Oh, sorry. can't do it just there. Hold it there. Number 2, control. There we go. Apologies. I have to click onto the whole entire cell here. So I've just pasted in to the input side. I'm going to pull this on down so we can just see what's going on. Delete this out. The input side here, my inputs IP0 down to IP15. They're just names. You can call them whatever you like. Right? You can call them the wall in front of me is blue. Whatever you want to call them, you can call them. Doesn't matter. I've called them this name here because it's going to reflect the name that's in my cyber input output. Now, where is that cyber input output? It's going to be here. So what I'm going to have here is something called the digital input. And I'm just going to call it DI. You can call it more if you want. You can call these names whatever you like. The important thing is the data type and where they're addressed to, if that's applicable. This here is a UDT-DI. And what I want to associate is this input. And by the way, if it's in the input field, it means that's a wired input, right? That's an input there that I'm going to read data in from the outside world. I'm going to be querying this IP0 all the time down to IP15, and I'm going to say, right, see this IP0? If that IP0 goes high, you go high. If that IP1 goes low, IP1 goes low. If IP6 goes high, IP6 here is true. Right? I want to match the two of them, but not just the inputs. I also want to do that with the outputs, my DQs. Now, these DQs are my digital DQs, my cyber DQs that are stored in my interface. There they all are there. They're not doing anything at the minute. They're just residing in a data type. Okay, and then what I want to do here is I want to associate it. If I send this DQ high in code, if I say that I want OP3 to be true, right? I want this block out here, this function, to send the associated output true. So that'll put 24 volts in out of the digital output card. So to name it, right, just for convenience, I'm going to do the exact same thing. I'm going to copy all of them, Control C. I can close that all together now, hopefully, and I'll click on into, I think it is the blue box there, yeah, V. And there they all are there. Take out this one. All right, so bearing in mind the input and the output up in these variables or parameters. So the way I like to think of these boxes, sometimes you see them called parameters, sometimes you call them variables. As far as the function goes, the parameters. As far as the code goes, the variables. The input are wired inputs to your cards or cards. Your output is your wired outputs, okay, at the cards. Now, this is an ET200 PLC. It's just something that I thought of. The ET200 PLC, the bit on byte 1 and then bit 5 you do not use. It's always true. So what I'm going to do is I'm going to go to into here, UDT-DI. Right? This is 1.7, 1.6, 1.5. 1.5 I'm going to rename as do not use, because it's always high on this PLC. All right, so again, what do you expect is going to happen? I've made a change to my UDT DI. When I come back in here, I get my pink field because I have changed something that resides at the very heart of my coding. I've changed a piece of data. So what I want to do is come back to Sean's PLC, the main PLC folder. I'm going to compile, and that we'll see will have fixed that, and so it has. And you'll also see down here I have 0 errors as was before, but them 3 warnings that I had that were associated with the security and the OPC UA being enabled are now gone. Right, so they come up in the first compilation, but not so much after. Okay, so now let's write a little bit of code. So to organize my code, I'm going to make a region. Let me just bring this up a wee bit bigger. You can see. So in this region here, what I'm going to say here is that I want the cyber inputs to emulate what the physical inputs are doing. So let's just write it like this. So cyber inputs, I'll tell you what, I'm just going to put in inputs. And then in the description, we'll say we want the cyber inputs to emulate what the digital inputs, or emulate, what about this? Emulate the state of the digital inputs. Cyber inputs to emulate the state of the digital inputs. And the format then for that, and actually put it onto another line here, we're going to say there that I want the cyber input, I am going to set equal to the digital input. This is a wee reminder. So I want the cyber input to be set equal to what the digital input does. All right. So cyber input, my first cyber input is di dot IP0. And set that equal to IP0. Done. Now, where have you got all that? Where have I got all that? Well, I'm going to do this a different way, just for the next one, right? So my first cyber input was di, belong to di.ip0. That's it there. My second one is this one here. I'm going to grip this flag on the outside and just drag and drop. di.ip1 space colon equal to, which is set equal to. Set that, I want that to do what this does. Execute, semicolon. And that's all it is. So the first time I just wrote it because it's quicker. Second time I drag and drop it, maybe to give you an idea of where I got the idea to write them from. Where did I get that syntax? So again, next one, di.ip2 is equal to ip2. Now you get the picture. And we can see a trend form. So hopefully this will make sense what I'm going to do next. Right, so I'm going to hit Control C, Control V, Control V, Control V, Control V. I'll stop it there for now. And you can see now what I'm going to do. 2 to 3, enter, 4, 5, 6, and 7, and so on. So this is hugely monotonous to do all this, granted, but we only have to do this once, and then the pain is over. It leaves the code so much handier. Okay, so there we are there.
So that makes sense so far. And maybe it may make sense to see why I named when I first came into here, I named these IP0 and IP15 instead of writing, some are extended, some would be retracted, whatever. It's just going to be so much easier to match these up and to change 1s to 2s and 2s to 3s at the very start. And then the template established, we have this kind of format, this structure done, we go back and we name it what we want, we compile, and then add-in changes will filter throughout the entire project. Okay, so what I'm going to do here is I'm going to pause this now and I'm going to bring this all the way down to 15 and I'll come back down, I'll come back in just on the 15. Okay, we're back in here again, just in time for me to do my very last one. This one here, of course, goes to 15 and 15. Now you will see one adjustment that I made in that. Obviously, for this one here, I'm not pressing it. I couldn't just change it to IP13, it's just the same as di.ip13. Indeed, that is on the di.ip13's place is do not use. That's why that's there. What I'm going to actually do as well is I'm going to change this IP13 here to, let's go just do not use there. When I hit that, see that it automatically updated there as well. So the changes up here in the function parameters, converters, whatever the fuck, will propagate down here. And that's it. So that's each one of them now associated digital inputs. Close up that region. Now what we're going to do is I'm just going to copy the whole lot of that input. I'm going to paste this in here, and I'm going to make this outputs. Okay. So in this one here, this is going to be digital output. So we reverse the order here. So I code, in my code, I read what's happening on the outside world. The outside world information comes in if the signal is extended, if the button's been pressed, whatever it might be. I read that, and transfer that into digital, into a cyber signal, into a cyber piece of data, and I code reads the data. Then I make decisions and code based on it, and I write like a response, what the code should do. And I write that in a digital cyber piece of data. In this section here, right, I want the digital output to emulate the state of the cyber output. So the cyber output is what I have told the code it should do in my if statement. If it's this and this and this, then do that. That's the cyber output. Here, I want the digital output to emulate that. So here, we swap the order. The digital output should be set equal to the cyber output. Now, so we have a mismatch in here. So there's numerous ways we can normally do this. I will usually just write it like this here. I'll change all these first ones to O's, as this is now set in my this is my digital output itself. So these are come into O's, right? Because that's what these here are. OP0, OP1, OP3, OP6, OP7, and down to OP10 now. Right, that is there. This one here obviously is going to need to be used. This is O, P1, 3, which is that one there. Right. O, and O. So those are my digital outputs. Must do know what my cyber output is. So this here is not a cyber output. Right? The way I'm going to do in this one here is I'm going to write a D2 dot delete and an O. D2 dot O. Why? Because that one takes me to this address, D2. When you put a dot, it mounds you into the tree a wee bit. D2 dot OP0. D2 dot OP0. Copy the first. I don't leave the hashtag, I usually do it. Control C. Control V. Control V. Control V. Control V. And just like this, little by little, we're now on our second file, and we've made our replacements. So this one here is going to leave it how it. O, P, 1, 3. The next one, V, and V. Job done. Now, I will say you could be massively careful with this because the most common error in this one here is that you've done like a D2.op4 and then you've done that op4 again, but you haven't updated circle from 0, 1, 2, 3, 4, 5, 6, 7, all the way down. Right? That's the most common error, and the symptom of that would be that even though you see that the code is saying that I've switched that output on, for some reason the output isn't on. It's because you've switched it on here, but it's then being overlooked by a subsequent line, which isn't switching it on. So be very careful now to make sure that you have each of them covered. 6 matches 6, 7 matches 7, 9 matches 9, and so on, okay? For your inputs and outputs, and make sure your orders are correct. So in the inputs, you want the cyber or the digital cyber input to emulate, to reflect, to match the state of the physical input. And on the outputs, you want the physical output to match the state of the digital input. It's just by virtue of the way we write the programs. And that's that. That's the cyber interface done. Now, I'm going to close that up. And the next big thing we're going to do is we're going to bring that function in to allow it to be executed. So bring it to the main OB. Right? This is our main program suite. Network 1. I'm going to write this in SCP interface. Alright, and then I'm going to just click the CPU interface and drag and drop it. So all our digital stuff, all our cyber stuff is down here, DI and DQ. Where do we get all that really separately? But where do we read and write our DI, DQ? Where is this information? What now? analysis here. For argument's sake, this is a, say for instance, cellular retraction sensor. If that's going through analysis, so here, if that's going through, I'm going to say that this is true. I won't say it's true here, but where do I want to store that information that is true? In the BI, and of course that gets stored in my data.bi. And similar for D2, I want to write that, read that from D2. Right, so that's it. So, in that code, I'm going to say, if the cell is retracted, then power on, I don't know, solenoid 3. So solenoid 3 gets powered on. Solenoid 3 is an output, but I power that on, and I said that true, decided that true. This block here is continuously reading this, and this is, this is solenoid 3 is going high. And it takes that information in. And it's going to say that if that output, say solenoid 3 is output 3 for argument's sake. Right, so it's this one. So this is where it's reading out of the data bank. If that's true, then the output 3 should be true. Output 3 should then it says OP3 true. Right? But where is OP3 going? There's OP3. That there, I need to address that now to my tag cover. Right? My PLC tags, run the regions here. DIs and my D2s, so these address strengths here. I need to associate them. That's just what I'm going to do just now. So, input 0 goes to percentage sign I 0 dot 0. Yeah. I'm going to control C that there, hit enter, and you'll see it there. We have a match. Control V, change that to 1. Control V, change that to 2. Control V, change that to 3. Control V, change that to 4. Control V, 5, 6, 7. Now, this one we'll be careful with, because this is same as our 0 point. Yep. This goes back to 1.0. Take a new copy. Number 1, 2, 3, 4, of course, I, 1.5 is a do not use. Right. So, that's that. So that's my placeholder in the function for rewired inputs. And this here is where the signal for the wired inputs comes from, in that address, which is on my input tag 0, here, byte 0, bit 0, down to byte 0, bit 7, which is tag 1, and then indeed tag 2, my second tag, which is byte 1, bit 0, down to byte 1, bit 7. Now, very quickly again, for my outputs, I'm just going to change that I to a 2 and put us back to 0.0 and copy Control C, copy the whole enter. Control V, 1, Control V, 2, Control V, 3, Control V, 4, Control V, 5, Control V, 6, Control V, 7. Now, that's that card saturated, so I need to go to my next card, which is byte 1. So, bit 0, coders. Control C. V, 1, enter, Control V, 2, enter, V, 3, V, 4, V, 5, V, 6, and Control V, 7. There's my digital inputs, all my digital outputs are associated in that CPU interface. So again, this interface is not necessarily, most people I don't realize actually that does this. This is just my way of doing it, because I don't tend to write functions out to wired addresses. I use this, with the exception of CPU interface, I just do not believe in writing the sequence data to read the digital input cards, the signal on the digital input cards and the percentage I zeros and the percentage I ones. I don't like it personally. I just like only one block to have that responsibility unless that's CPU interface. As I will do is I'm going to read and write to data. this gives me an advantage where I can say that that input, for instance, can go high if the physical signal goes high, goes through. So for instance, one of these inputs here on the cyber side is indicative, it reads the limit sensor for signal B. Right? But again, so rather than which it go is a push button. It's reading the state of a push button. So I could say somewhat I want the cyber bit to go true if the button is physically sent a 24 signal to this wired input address. And I said, now what I can also do is I can write encode or I can either encode or I can send it through using some other function. And importantly as well, I can override it in no data. I can override it here in no data. Specifically on the output. So the output is going to go high if the data input goes high. But what I could potentially do in OCR is that if I run online, I could force that to go high. I don't know those force tables for these things, but now I can, to get onto a force table, we need to be looking around PLA. But this now data block, I can, because OPC UA is 11, I can now access this, I will be able to access this data block from anywhere once I have the IP address, the port number, and indeed once this block is enabled on the OPC. The name on the block that I think to just think about before I close off this video is that I can enter brings up the properties of this. You'll see the attributes of this my data block. After those block access is checked, make sure it is checked. If you take the check off it, it'll still work. But what you're going to do here is you've added in addresses, which we don't. I'm not really worried about adding addresses into this one. If we are doing so TCP communications, so peer-to-peer communications, we have a separate block there that is that's not optimized for the addresses which you need, but other than that, we just let the PLC deal with the organization of the block just in an optimized fashion. Now, last thing I want to do after I do the function, so every time you write a function, every time that you update your main program scope, it's a good idea to compile. Make sure that we have no errors. Set that compile again. No errors, no errors, that's good. And what we're trying to do then is let's just download this down into the PLC so we have a backup copy somewhere. Let's see what I have. Ethernet connection. Let's see if we have a problem here. This is probably because I played my Ethernet cable after the last video because my Wi-Fi went down with it. I could see the action cancelled before download. Let's see what we can do here with this. Yeah, I'll tell you why that is. It is because... Let's see that here. 1 second, folks. Just in case there's anything across this. And this one here is normally because there is a device up here with a different article number can't identify it in the highway catalog. And that's likely what it is. So just see if I was to going up this video and I did a little bit of debugging that is always update accessible devices. A little bit of debugging that is always is always helpful. So systems and time. I'm not seeing the PLC just now. So 1 second everybody. Showing our VPN connection is just not made. So it is a definitely something to do with me putting up together. Just try one more time. That is down Pt200. Let's try it one more time. Just the connectivity clearly wasn't made properly. Let's try it again. So let's do another compile just in case. Download. looking at the start shots. That is there, load. This is going to run the always connect the first simulator down. It's just showing that there is program blocks and that PLC is configured in a particular way. That doesn't match what's out here, so it always continues without synchronization. I'm just scrolling down to make sure there's no print fields, but if the load button is active, it usually means you're good to go. Let's load that. Okay. So that loaded, so we're on line now. That line right there, back up, we're loaded down into the PLC. But, so that'll do for this video here. We're going over 40 minutes here, so it is a little bit long, but yeah, we'll kind of quick that in the next video. What we do is we're gonna change our inputs and output tags in the UBT, and the image convention in the UBT to more accurately reflect the equipment that is likely to be encountered in an automation region task, and we'll see how that propagates through both the load data block and through the other function blocks. We also run it in the output blocks and output function, show you how to do that, as well. We've got in a sequence of one, at least. We write out a starting template for that. And in the following video, we'll write out the management block, we'll put it all together, and then eventually we'll look at an example. Okay, so thanks very much for tuning in. I hope you enjoyed the video. Please let me know what you think. If there's any questions, certainly shoot me a comment, and I'll get on it right away. And if I don't hear from you, so I hope I'll see you in the next one. Thanks very much.